lock that is available to us, right? When I say single lock, meaning that either you can use it for a single global variable or you can use it for any particular resource. For example, if you are using an Ethernet port between multiple processes, right? Which process will access that Ethernet port? How do you determine that? Right, so you use mutex lock. So whichever process is able to acquire a lock, that is the process who will be getting the access to that, right? So in order to use mutex, first, generally for any global variable that we want to use, we have to do the initialization, right? So for mutex also, there is an initialization function that we will have to execute. We set mutex init, and then this is the type of mutex data. So whenever you use this type of data, the operation performed on that type of data will be atomic. What do you mean by atomic? Atomic means that setting of the value, increment of the value, decrement of the value, anything that you do will be done in one shot without having any other process access to that variable. Okay? That is what atomic means. Okay? So we use the mutex variable, right? And then if you want to pass some attributes which we generally don't need to, so we would use the null value here. You would declare you will initialize your mutex variable. Once you are done using the mutex, you need to destroy the mutex variable. So this is more like doing malloc, allocating memory, initialization of the variable. Okay? So operating system internally is doing the malloc when you do the init. When you do destroy, you are basically freeing up the space. That is what you are doing, right? So you have to use these two functions in order to use the mutex variable first. Now, once you have initialized the mutex variable, how do you use that? Is using these three functions, right? Mutex lock. So whichever process wants to acquire a lock, or whichever thread wants to acquire a lock, will issue the lock system call or function, right? You will see that it says that it is a blocking call. What does it mean? It means that if one thread has initiated that function already, and if the mutex is locked, right, and then the second thread tries to call the same function. Now you can only acquire a lock once for a single mutex. You cannot acquire multiple locks on the same mutex. Which means when the second thread comes and tries to execute that code, it will be blocked. Okay, it will be blocked, meaning that is the blocking call. Once you have the second thread calling this function, you cannot execute any further code after that. Okay, that is what we call as blocking code. If you don't want to use that blocking call, there's another one called try lock. Okay, so try lock can be called by the second thread, and it is not going to be blocked, but if the mutex is already locked, then the function will return, but it will return an error code called key missing. So the return code can be checked, and you can check if it is key missing. That means that the lock is already faced by another thread, and so this thread is not going to be locked, but it is going to be again, after some time we can again try that. That is how that mutex will work. And then once you're done using the mutex, you can use the unlock function to release the lock on the mutex. Okay? So these are the three functions that you can use for locking mechanism. Okay. So here is done, but as you all know, you always look at all the things practically, right? How does it work? So I have two examples here. The first example is for the race condition that we have seen earlier. So we have two threads. Both the threads are calling the same function, character function, right? function, as we know, is displaying a single character on the standard output device. Right? Single character on the standard output device. And you will see that there is another thread here. So in this thread, we are just displaying 0 to 9 continuously. In the second thread, we are displaying 8 to 10 continuously. Right? So this is the two threads that we are executing, and it is following a common function. So it means that since the locking mechanism is not used in the function, we are expecting a race condition when we execute the code. So let me start the virtual box. Okay, so let me execute that function. Thread race condition without mutex. Right, so we are not using mutex here. We are not doing any locking. Right, so when we execute this code, as we have seen earlier, what happens is that the characters and the numbers are doubled up. Right? Characters and the numbers are doubled up. Why? Because both the threads are accessing the same shared device, standard output, right? And both are trying to write using that, right? So this is the example where we have the race condition for standard output device using two threads. Now what we will do is we will implement the mutex, which is a locking mechanism. So if you look at the thread function, which we are calling, what we are doing is before the loop, right? Before the loop, we are saying lock the mutex, right? And of course, before using the mutex, you need to initialize that. Right? So we declare a variable by mutex, and then that obviously is a global variable. It will be initialized using this function, and then when the threads are created in the thread function, you have the lock. Right? So when you lock just before the for loop, this for loop will be allowed to be executed only by a single thread. Are you getting the point? So one thread goes in to the function, it acquires the lock. Right? It acquires the lock. Now let's say the second thread also came into the function. It tries to acquire the lock in that mutex lock function, but it will not be able to acquire the lock because that mutex is already locked by another thread. Okay? So the first thread gets a lock, second thread is waiting. First thread executes the for loop, it then executes the unlock function. As soon as it does the unlock, the second thread will be able to acquire the lock, and then it will execute the for loop. So the point is, only one thread is allowed to execute the for loop, and that for loop is what we call critical section code. Okay? For loop is what we call critical section code because it has the device or some global variable which is being shared by multiple threads. Right? So critical section is something where the code has some global variable or some devices which are shared between the threads or processes which passes the race condition. And to avoid that race condition, you use the locking mechanism. So when I execute this code hundreds of times, you will never find that there is a jumbling of the characters in the output, because only one thread is going to be allowed to do the follow. Otherwise, the second one will always have to wait. Okay, so this is how we can eliminate the race condition. Right, so if I execute hundreds of times, so only thing you will see is that in some case the numbers will be up and the characters are zero. Some case characters may be up and numbers are zero, but you will never find the jumbling together. You will never find that the characters and numbers are mixed together in any scenario. Never. Because once one thread function finishes, then only the second thread goes to the model. Otherwise not. And this is how we are able to do mutual exclusion. Remember I told you two concepts. Critical section code and mutual exclusion. Critical section is the code which is sharing some device or global variable. Mutual exclusion is implemented using locking mechanism, one of which is mutant. Any questions? Clear to everyone? Okay. Sorry. All right. So now let's look at the problem with the mutex. Okay. So obviously, when you have the locking mechanism, you could have the problems here also. So one of the problems that you find is deadlock. Okay. How the deadlock can be caused? Let's say the same thread has a code in such a way that it is trying to lock the mutex two times from the same thread. Right? So before releasing the first one, second function may be called from the thread is again trying to lock the same mutex. So you end up in the deadlock situation there. Right? The second situation is what we call circular locking. Right? So in the case of circular locking, basically your mutex 1 is locked by, let's say, thread 1, and then thread 2 is trying to lock mutex 1. Okay? Thread 2 has a lock on mutex 2, but then thread 3 is trying to lock the mutex 2. Thread 3 has a lock on mutex 3, and thread 1 is trying to get a lock on mutex 3. So basically there is a circular way. And there is a circular way. If that happens again, you have a deadlock situation. So obviously one of the solution is apply the try lock function. There are other kind of problems that mutex cannot solve. Okay? So there are problems which are called reader-writer problems or producer-consumer problems. You can also call it as a producer-consumer problem. So in that case, there may be multiple reads happening. Right? So for example, if you look at the operating system, in the operating system we have a process table or a thread table. Right? Now there may be multiple processes or multiple threads of the operating system trying to read that table. And there may be multiple processes trying to update that table. So it is basically reader-writer problem. Right? So you have multiple processes or threads trying to read the same table as well as trying to write. We cannot implement locking mechanism using mutex for that. So there is a special type of block available for reader and writer, which we will look at next. There's another kind of problem which is called dynamic philosopher problem, which again I will come to that. Again, this kind of problem cannot be solved using the mutex. So that is solved using another type of block called semaphores. Okay. So I don't know if you have heard about the word called semaphores. Computer organization? Anyone? No? No? Okay, fine. Okay. So what is different between mutex and reader writer law? So if you have some entity where multiple processes or multiple threads are trying to read, right? Multiple reads should be allowed, right? Because there is no problem. Remember, I told you that whenever you have two reads coming together, there is no issue. Whenever write and read are combined, that is where the issue comes. Right? So either read after write, or write after read, or write after write. If these three conditions are occurring, then you have an issue. Right? So we want to basically do mutual exclusion for that. So what happens is that multiple readers should be allowed to have a lock on mutex. Right? But in reality, mutex only can be locked once. Whether it is a reader process or writer process, it doesn't know. It doesn't know. So even if you are trying to read the same value, but if you apply a lock on mutex, you can only get locked once. You cannot get it multiple times. So again, the mutex will not work there, right? So how do we do that? Second thing is only one writer process should be allowed. Only one writer, not multiple writers. Or when there is a writer process has acquired lock, no other reader process also should be able to acquire the lock. Because somebody is updating the table and the other person should not be able to read that table. Okay? So reading and writing are mutually exclusive activities. Okay? Two reads, fine. Read and write, no. Right? Write and write, no. Right? So only one writer process should be allowed to acquire a lock. Right? And as I said, reading and writing are mutually exclusive. So that means when the reader lock is there, the writer should not be allowed. When the writer lock is there, reader should not be allowed. Okay? So these conditions have to be met. And therefore, the normal mutex lock does not work. So what do? We have a new type of lock, which is provided to us by the operating system. And that is actually called pthread underscore rw lock underscore t. That is the type of the lock we have. Pthread underscore rw lock underscore t. This is the variable that we are initializing, right, using pthread rw lock init. Right, so again you are just allocating the space here. This prod will be reallocating the space, right? When you look at the lock and unlock functions, now we have two lock functions, not just one. Right? We have the read lock function and we have the write lock function. Okay? So when the read lock function is issued by any thread, if there is already a write lock on that lock, then the read lock will go into the locking wait. Okay? If there is already a read lock on this variable, then the writer will go into the locking wait. Right? If there is a reader lock already there, and if some other thread does the reader lock, then it will be able to lock again. So multiple read locks are allowed, right? So if you have multiple threads issuing the RD lock multiple times, all of them will be successful. Okay? So that is the basic difference between this lock and the mutex. Right? So this is the special lock where we can do reading and writing activity together. So to show you an example, and again, you have the unlock and then you have the try lock functions also, similar to the mutex one. So to show you how this can be used, what example I've come up with is the activity on your linked list. So for example, we have a list which is being updated and which is being read. Okay? And maybe you are keeping track of some information there in the linked list. I hope everyone is is familiar with linked list? Yes. Okay. All right. So if you see that function has a printing of the linked list, right? So let's print head, right? So we are just providing the head pointer, and it is just going through the iteration of the linked list, and it is printing the all the. Let me just look for that. Right, so we are just starting from the head node, and then we just print every element from that head node onwards all the way up to the null value. Right, so that is what we are doing in the print list. And so in that case, we are acquiring the read log, right? Because we are just reading the linked list, right? Now, if you see the main function, we have the this function is called reader rw lock, okay, and that function is called twice using two different threads. Okay, so there are two threads which are executing the read activity. Okay, so we are printing the linked list twice on two different thread functions, and then there is a single thread which is executing the write function. And in the write function, I think inserting data or something like that, deleting the data. In this case, we are just issuing the write block, right? And then we are doing some operation, insert, remove, whatever, and then we are releasing the write block. So the point is, during this process, no other reader will be allowed, no other writer will be allowed. Okay? During that printing of the linked list, this block will not be allowed. This block will not be allowed because printing is a reader, and writer and reader cannot go together. Okay? So this is how we can use read write block. Okay? This is how you can use read. So whenever you have a single shared component, for example, as I said, you can take an example of let's say producer consumer where you have a queue, right? One process is generating the data, putting it into the queue. Second process is trying to read the data from the queue. Right? That is why we call it as producer consumer problem. So any such problems that you may have, you can use read write block for that. Okay? So again, the output will not be interesting, but you get an idea. So it's just trying to display all the linked list data and while it is trying to update it. So as I said, the output is not very interesting, but understanding the code will basically understand that how this read write block works. Right. So producer consumer type of problems you can implement. So in the operating system only, if you consider there are several examples or use cases for the logs, memory page table. Right, so there is whenever the memory is allocated by operating system to different processes, right? So you have code segments, you have data segments, and these memory allocations for which it has to again maintain a list or a table, right? So that is where you can use the reader writer logs. Second area, process control blocks. Multiple threads may try to access the process control blocks for different information. Let's say reading of open files, right, or status of the process and so on, right? So you can use again the locking mechanism there. Kernel thread table, if you have KLT that you are using in your system, kernel has thread table inside, as I mentioned earlier. Multiple threads may try to access the same thread table. Okay, so then you can use reader writer locks there. So kernel will be implementing reader writer locks for accessing the thread table. Okay. So any shared resource that you may have, right, in your system, you can use reader writer lock. Any questions? Okay. So Mutex can do certain things, reader writer lock can do certain things, but still there are certain other things that is not possible even by these two types of clocks. Okay. One of the example is very famous example generally given in most of the operating system books is called Danny philosopher problem. Okay. What is the Danny philosopher problem? Basically, the point is that there are 5 philosophers or n number of philosophers here, and then there's a food here, right? Think of the philosopher as fork or chopstick or whatever, right, next to the food. Now the point is, if this guy wants to eat, he needs more of these. He needs more of this. Similarly, when this guy wants to eat, he needs more of these. So these are the resources that are required to be consumed by this philosopher if that person wants to eat a food. Okay. So you have a resource and you have the process or some thread who is consuming that resource, who wants to consume that resource. Right? But here it is not in the fixed format of mutex or redirect. So here you are not saying that multiple people can read, multiple people can write or not. Right? So that concept does not come here. It is the concept is number of resource and the number of consumers, right? Who is going to be consuming that resource. So for this kind of things, we have a special law again called semaphores. Okay, semaphores. I'll give you an example of the real example. Let's say in our system you have 4 USB ports. For example, I have 4 USB ports. Right? Now, n number of processes wants to access the USB port. Right? How does operating system maintain which process has access to which USB port? Or how many ports are available to be locked? So you have a resource of USB port, right? And then you have the threads or processes trying to access that resource. Right? So you use the semaphore and say that okay, you have access to 4 resource and you have n number of process which will then access the resource using semaphore. Okay. So again, if we take a look at an example, it will be clear to you. So there are 2 types of operation that we normally perform on the semaphores. One is called wait, the other one is called signal. The wait is going to be basically reducing the value of semaphore, and the signal is going to be incrementing the value of semaphore. Okay? So it means that here you are acquiring the lock, this means you are releasing the lock. Okay? But you have n number of locks. You don't have one lock, you have n number of locks. Right? So in mutex you just have a single lock. Here you have n number of locks. So for example, again, if I go back to the USB example, 4 USB ports, you can acquire 4 locks on that USB resource. Okay? So that is why we have this counting thing. Okay? So semaphores can be used again as a binary semaphore or a counting semaphore. When you say binary semaphore, it is same as mutex. So mutex is an equivalent of binary semaphore, which means you can have a single lock and single release. That's all. Single lock, single unlock. Right? That's a binary semaphore. Counting semaphore is the one which is more evident, more useful because we can share the resources. Right? So as I said, processes can be sharing the processor. You have 6 cores on your system. Let's say. Which cores are allocated to which processor? How do you know that? Or how many cores are available? How do you know that? So operating system has to keep track, right? The count. You can use semaphores for that. Multiple network devices, forces sharing the task, whatever. Any shared resource that you have, n number of shared resources shared by m number of processes can be using the semaphores. So I think binary semaphore is simple. It's like mutex. We just lock once and then we release once, and that's it. let me actually take you to the actual example later. So, okay. So in semaphore, this is how we initialize the semaphore, right? You have three parameters. The first parameter is the variable, the semaphore variable. Just forget about the second parameter for now. Third parameter is the value with which you want to initialize the semaphore. Okay, so as I mentioned, semaphore can have multiple locks, right? So that means value can be 5, can be 10, can be 1, depending on how many resources you want to lock using semaphore. Okay, so that is why we are calling it as a counting semaphore, right? So if I say 5, I can increment 5 times and increment 5 times. That means I have 5 resources which I want to control using that semaphore. That is what I'm doing. Okay. Second parameter, which we call P shared, that parameter is normally, see, we know that processes do not share data area, right? It has its own data area. But if you want to share semaphore between the processes, there is a special memory allocation that the operating system will do for sharing only that part of the memory between the two processes using that second parameter. That is called P-shared variable. So again, if you don't understand, don't worry about it because that is not something that you will be using in this specific course. But you should know that there is a way where you can share the memory between the processes, especially using this variable. Okay? And then you can destroy the semaphore once you're done with it, right? So for the operating system, instead of signal, they have given the method called post. So post will increment the value of semaphore and wait will decrement the value of semaphore. Okay. So let us take an example of semaphore first. So in this example, I'm using semaphore as more like mutex, but I just wanted to give you an idea as to how we initialize that semaphore and how we use them. So what we have done is that we have used this variable called semaphore, which is our semaphore, and then it is initialized with the value of 1, which means I'm saying that there is only one resource that I have, which I want to get a lock on. In the main function, we have a single thread function which is being called, and what we are doing is we are basically either getting access to the standard out device using either thread function or using the main thread. So between the main thread and the thread function, the semaphore is locked. So for example, if you see here, right, unless you press any key, the semaphore is available to the thread function. So thread function will be able to get lock on semaphore. It will be able to keep on printing that message, right? And then it will read again in the next iteration. It will keep on displaying the message. As soon as I press the key here, the main thread will get the lock. And the main thread will get the lock. Once the main thread gets the lock, the child thread will not be allowed to get the lock on semaphore because we said that the value is only 1. Value is only 1. Right? So now the child thread will not be able to print anything. So once I press a key here, this lock is in the main thread. Again I press a key here, the lock is released from the main thread, and then again the child thread will be able to acquire the lock. So basically the shared resources get standard output again, but then we are sharing that between the child thread and the main thread. That is what we are doing. sorry, semaphore. So until I press any key, the thread function will keep on displaying this, right? Once I press a key, now the main thread got a lock. The main thread got a lock. So because the main thread has a lock, the child thread is not able to operate the lock on the semaphore. And so child thread is not executing. It's not displaying that message. Okay? So currently the lock is with the main thread. Again I press a key, the lock from the main thread is released, and again the child thread is able to acquire the lock and is able to. Okay. So this is again similar to mutex because I'm just using a single value for semaphore. But the next example that I'll show you will be for multiple resources, multiple semaphores. So let us assume that we have two global variables, I and j. They are the shared resources. Okay? And then I have two functions, function 1, function 2. They are using those shared resources, I and j variables. Okay? So in function 1, we are incrementing or adding the value of 2 to I, and in function 2 we are adding value of 2 or whatever to j, and we want these functions to be executed by multiple threads. So we have 4 threads. The first 2 threads are executing function 1, the third and fourth thread is executing function 2. Okay, which means that when you execute these 2 threads, they will be competing for the shared variable I. When we use these 2 threads, they will be competing for shared variable j. Okay, so the example that we are showing you here is you have 2 shared resources, but you can use multiple threads to share those resources as well, right? So, like for example, USB port and network interface, right? Ethernet port. You can have those 2 shared resources can be shared between multiple processes. That is the kind of example that we are showing here, right? So using this, basically I want to show you an example that these 2 threads are accessing I variable at the same time. These 2 are accessing the j variable at the same time, which are the global variables. And so, for accessing those variables, we are trying to get a lock before incrementing the value, and then after incrementing the value also, we are releasing the lock. So that is what we are doing. So let's say if we have USB port access or something, or network port access, that is what the code you will do here, right? So in case if you were trying to do something or something with the USB port, you will put in that code over there. That will be your shared resource, right? So that is the kind of code that you can use with the semaphore. Now let me show you this code, and I'll not try to explain this code here, but I would want you guys to take a look at this code before the next class, and I will explain maybe in the next class, or if you have already understood the code, maybe one of you can explain how the code works. Right? So what this code is actual implementation of the dynamic philosopher problem. Okay. So I'll give you just a brief idea. So philosophers have 3 states: hungry state, thinking state, and eating state. Okay. So hungry, thinking, and eating. Those 3 states we have, and we have the put fork and take fork functions, right? So that is where we are ensuring that if one philosopher takes the fork, one of them on the left side, let's say, the same philosopher should be able to take the port from the right side. If that philosopher does not have access to the port from both sides, that philosopher will not be able to lock anyone. Okay? So we are making sure that both are available or none are available. Okay, that is what we are making sure in the put fork and the take fork example. This is the loop for all the 5 philosophers. So as you can see, they are doing take fork and put fork. And then this is where the initialization and the thread creation is happening. So each thread is each philosopher. Okay, each thread is each philosopher, and each philosopher has 3 states, thinking, hungry, eating. So whenever a philosopher is hungry, that philosopher should be able to take 2 forks. If that philosopher is not able to take 2 forks, then it has to wait until someone releases either the left or the right hand side of the fork. As soon as that person releases it, then this person will be able to take more forks. So that is the code what it is doing in essence. But I want you to go through the code and try and understand yourself. Okay? Because I can explain, but if you work for it, you will be able to better understand. Okay? If you are in doubt, definitely we will discuss in the next lecture. Right? Okay, so I think that was the last slide on the concurrency control. Any questions on the training environment? How does threads work? How it is different from process? How does the locking work? Yes. How does only one core can do multiple threads? Yeah, correct. So, so if you recall, I had mentioned that it would do time to async. I forgot the marker. Uh, we try to. Okay, so basically what will happen is each of the core will be assigned certain amount of time. So let's assume that each core has this time slice. 0, 5 milliseconds, 10 milliseconds, 15 milliseconds, 20 milliseconds, and so on. Right? Now, let us say that you have 5 threads that you want to execute. Right? And let's say you have 2 cores. So you have C1 and C2. So at, let's say, time 0, you get T1 and T2 here. Right? So thread 1 is allocated to core 1, thread 2 is allocated to core 2. Once the first 5 milliseconds are over, which is your context switch time, right? Your context switch time, then the operating system will say that, okay, you guys are done, you need to context switch. So the cores will be unallocated, those threads status will be saved. So PSW, stack pointer, and stack will go into the memory, right? Aside, and then the next 2 threads will be allocated to the same 2 cores, right? So let's say here T3 and T4 will come. Again, time is done. So now let's say T5 will come, and let's assume that T2 comes, right? So now T5 is allocated to core 1, thread 2 is reallocated to core 2. So again, it is not always necessary that whichever thread was running in whichever core in the previous time, the same core will be allocated to the same thread. It's not always like that. You can have different threads going to different cores depending on the availability. Does that make sense? Only after? No, no, it is not. See, if the thread is completed, then there is no need to allocate T2 to core 2 again, no? Right? There is no need to allocate. So, what I am trying to say is that it will, let's say now here, let us say here, T2 is complete now. Okay, if T2 is completed here, then let's say T1 goes here and T3 goes here. So whenever the thread is completed, that does not require any allocation to the core. But let's say, in this case, let's say T1 is taking 25 milliseconds. So every time when there is a time to allocate thread T1 to core, right? So let's say, the first time it took 5 milliseconds, second time it took 5 more milliseconds. So like that, it will continue, kept on allocated for 25 milliseconds. And then the thread will be completed. Okay, understood? Any other question? Okay. So let me briefly start with the next chapter. Have you guys studied networking before? No? Okay. Are you aware of IP, Internet Protocol, IP address? Maybe? Briefly? Little bit? Okay. So, I know that you're not studying networking. So what I'm going to do is, I'm also going to teach theory part of the networking a little bit, because otherwise you won't be able to do the programming. Right? In order to do the programming, you have to understand the theory part. Right? So first I go through the theory of networking area, and of course I think you do have computer networks in the sixth semester or fifth semester, right? Yes. You haven't looked at the course material? So what is a network, right? How does network work? How does internet works? How does the applications on the cloud work? How does your database work? Everything, all the applications that we use which are using the network is using these concepts. Everything, right? So most of the application that we use works in what we call client-server model. Client-server model, right? So client is something which is trying to access some resource, and the server has the resource. So for example, if you are using a database, then a database server has the resource which is in form of database, and then the client is filing the query, SQL query, right? Trying to access that resource. Did you study database? Yes? No? Okay. Maybe I should not use those concepts then. You obviously use web pages. Right? You're using websites. DHCD website. Right? You go to eCampus portal. Right? So eCampus portal has a data, and you see your grades, you see the courses that are allocated to you and all that. So there are all these sources, which is with the web server. which is housed in campus or on the cloud. So basically the resources that you have are managed by the server and the clients are accessing that resource over the network. That is basically what we are doing, right? So server is the process with one or that can have one or more clients. Server will be managing the resources. Server provides the services to the client, right? And then the server is activated by the request from the client. So the client will be requesting something to the server. Server will handle the request, will be responding to the client, and then the client will be handling the responses. This is generally how all the network-based communication work. So in the computer network area, uh, you could have different type of network depending on the uh, geographical location in a way. Okay. Uh, these days there are more buzzwords also there. For example, PAN is another type of network, personal area network. Okay. So personal area network is your phone, router, your laptop that you may be using at your home. And so you have a small router at your home and you connect all devices in. And so they call it as personal area network. In the range of maybe 10, 15, 20 meters range. Okay? You could have a system area network or a storage area network where you could have multiple CPU racks and multiple storage racks. So multiple disks are there and multiple processor racks are there. They are all connected together in a single system. And that is called system area network or storage area network. You have a LAN, local area network. Generally, local area network refers to something that is like maybe campus wide or building wide. Okay, so within a building, all the devices are connected, right? So that, for example, everything in CP building is connected to a single network. Right? Everything in the lab building will be connected to a single network. So that is what we generally call it as local area network. Okay? Wide area network crosses the city boundary, country ground boundary, and so on. Right? So whenever you want to connect from, let's say, some location from here to, let's say Mumbai, in south somewhere, or even across the ocean, right? When you want to go beyond the country, right? So all of that generally comes under wide area. Internet is generally used to refer earlier as internet network. Now for short we use internet. All the devices that are connected to internet is generally what we call host. HOST host. Hosts are all the devices which are connected to the network, internet. Okay? And internet has a global address. Global address. So every single device, for example, how do we know where each one of us lives? Right? There has to be unique address. Unique address. Right? Your address cannot be same as mine. Otherwise, how would we identify that this is a different person and this is a different person? Right? So you have to have a unique address. So every single host, billions of devices that are connected on the network, they all have one unique address, IP address. Internet protocol address. Okay, IP stands for Internet protocol address. Okay, so IP address is always unique for all the devices that are connected on the internet. Now, how the internet was built, or how is the internet built, right? So as I mentioned, there's a proximity where the devices are connected. So in the small proximity, you have, let's say in this room, only few devices are connected. Then you get 4 devices connected between this room and the other room or the building, other building, and so on, right? So depending on the size of the area, there are different devices that needs to be used. different devices that uh, the first smallest device that generally we use is called hub. Nowadays, nobody generally uses hub. Everything is router because router takes care of hub also. But in olden times, we used to use hub, and hub usually spans in the roof or the floor on the building. It basically works at what we call the Ethernet address level or a MAC address level. The name of the address that we use is called MAC address, and it is this 16 byte value. 16 byte value. Each of your computer will also have the MAC address, and you can actually take a look at it. So, for example, on the Windows machine, if you run a command ipconfig all, whatever you see as a physical address here, these physical address are nothing but the MAC address. So every single network device that you have on your computer, on your mobile phone, every single one of them has a separate MAC address. So for example, your Bluetooth will have a MAC address. Your Ethernet port will have a MAC address. Your USB port will have a MAC address. So every single network port that you have on your system, every single one of them will have a MAC address. Okay? And that is the physical level address that we have. Then, once you span across the roof and then go to the building level, then you had something called as bridge. So what bridge was doing, it was connecting multiple hubs to go across the buildings. And so, again, in the olden times, we used to use hubs and bridges. Nowadays, everything is replaced with the routers. And then finally, there was a router. Okay. Now the function of bridge and all of them is done by router. So the function of router is to connect multiple LANs or multiple local area networks into a wide area. So let's say if you want to connect from here to let's say Google's IP, right now the Google server may be located in Singapore. Okay. When you try to access google.com, then you are trying to access actually the server which is sitting in Singapore. So how are you able to connect to that server from here? Right? So every area will have a local area. So for example, Ahmedabad, there will be a local area here. From Ahmedabad, you will be connecting to let's say Mumbai. They will have a local area. So there will be a hop or connection between Ahmedabad and Mumbai. Right? And then from there, you will go over the ocean and connect to Singapore. Right? So every single segment will have a local network, and then each of those local network is then connected via router. Okay? So router is not only used within the home, but it is used across the country also, connecting different networks across the country, across the city also. Okay? You can have different connection type also. For example, if you connect from your mobile phone, right, you could use the Wi-Fi, or you could use your regular 4G or 5G connection, right? So each of them they have this different protocols running. So you could connect using Ethernet, you could connect using Wi-Fi, you could connect using your 4G network and all that, right? So each one of them will have a different type of connection. And the router is the only device which is able to understand all this. Okay? Hard and bridges, they will not be able to understand those differences. And therefore, generally now we are not using them. Right? Router is the one which is able to understand, so we are using them.
Uh, I think this particular slides I can skip because you don't really have to know this for programming part.
Let me just cover this slide and maybe one more slide, just to give you a basic idea, and then I'll stop. So, whenever you use internet, there are two types of uh, technology that is used. One which we are familiar with, which is called internet protocol. Okay. So, see, basically what happens is when I'm connecting to, let's say, Google server, I'm sending the data to Google server, and Google server is responding to me with that data. Now, whatever data I'm sending, right? Maybe that data is 10 kilobyte data. Okay? But at the time, I'm only allowed to send, let's say, 1 kilobyte of data, which means I have to divide that 10 kilobyte data into 10 different packets, 10 different buckets. And those 10 buckets, each of them will have to go to the Google server. Now, it is not compulsory that each of those packets will be reaching Google server one after the other in sequence, because each of those packets may go to different routes. Let's say one goes from here to US and then comes to Singapore. Another one may go to Europe and then come to Singapore. Other one may just go to the south and go to Singapore, whatever. So it is not compulsory that each packet will follow exactly the same route, right? Which means it is possible that some packets may get lost, some packets may get duplicated, right? So the receiving end will have to ensure that all of these packets are collected and a single 10K data is on. Okay? So sending the packet, sending the individual packet of 1K is done by IT, Internet Protocol. Okay? But you need a layer above that to ensure that all the packets are received and they are received in a particular sequence. Combine them in a particular sequence. Okay? That is one level above. And that is done by TCP. So in the internet, you have two types of protocols that is used. Internet protocol, and then the second type of protocol which we call transport layer protocol. Transport layer. Okay. So transport layer is the one which is ensuring the handshaking between the two sides. Okay. Handshaking between the two sides. IP level is just concerned about sending the data, that's all. So combining those two, we are able to then send and receive the actual messages, whether it is large or small. Okay. So this is how usually we.
And I just put this picture so you understand how.
Basically, so let's say you have a client which is creating the transport layer packet. It is then sending it to the IP layer. IP layer is actually sending the data to internet outside, right, of your building. Someone is taking the data and sending it to the right place. Let's say this is your server side. The server side takes in the data. Again, this data is collected in the IP layer, collected by the transport layer, and then sent it to the server. So this is every single time that you are trying to access any of the server on the website, this route is being taken, right? And the response then will come from there to here. Okay, so every single time that is what is happening. Okay. So let me just stop here. I think we'll continue in the next lecture. Any questions? No. First,
Sir, how is IP unreliable?
Okay. Thank you.